Hello everyone, my name is Rwemalika and welcome in this session where I will present the work we have done with our team from the University of Luxembourg for our paper called Data-Driven Simulation and Optimization for COVID-19 Exit Strategies. Before diving in the heart of this talk, let me briefly introduce the Luxembourg COVID-19 Task Force, which this work is a product of. The task force gathers researchers from different areas with a common goal: help decision makers to tackle this global crisis. In a nutshell, the task force is divided into three axes. The first one, molecular level, aims at understanding the biology of the virus. The second one, individuum level, focuses on patient monitoring. And the last one observes the epidemiology of COVID-19 at the population level, the level at which we will conduct this study. The creation of this task force and many others around the globe was driven by the rapid spread of the coronavirus SARS-2 and the major challenges it created that led almost all governments worldwide to take drastic measures to respond to the tragedy. Chief among those measures is the massive lockdown of entire countries and cities, which, beyond its global economic impact, has created some deep social and psychological tension within populations. While the adopted mitigation measures, including the lockdown, have generally proven useful, policymakers are now facing a critical question: how and when to lift the mitigation measures. Indeed, when talking about lifting mitigation measures, policymakers need to devise exit strategies. A carefully planned exit strategy is indeed necessary to recover from a pandemic and minimize the socio-ecological impact, such as job losses, lower economic growth, leading to an increase of households entering into poverty, but without risking a new outbreak that would lead to the more people getting infected and hence resulting in more hospitalization and ultimately more death. This leads to the question: how can the scientific community help policymakers to find an optimal answer accounting for all these different conflicting objectives? To answer this question, we propose to provide a tool for policymakers to easily generate exit strategies and evaluate the impact. An exit strategy can be represented as a schedule of measures that will impact the way the disease will spread. The first step in this endeavor is to use the classical mathematical modeling tools to predict the effect of public health interventions. Unfortunately, such models are known to be sensitive to some key parameters, which are usually set based on rules of thumb. Hence, we propose to augment epidemiological forecasting with actual data-driven models that will learn to fine-tune prediction for different contexts. We have therefore built a pandemic simulation and forecasting toolkit that combine a deep learning estimation of the epidemiological parameters of the disease in order to predict the number of cases and the number of deaths. Finally, we propose a policy search module based on a genetic algorithm to suggest the best policy out of all the available outcomes predicted by the model. The goal of the algorithm is to minimize the health impact while at the same time minimizing the socio-economical impact linked to the reduction of activities created by the lockdowns. As we already mentioned, mathematical modeling offers public health planners with frameworks to make prediction about the spread of emerging diseases and assess the impact of possible mitigation strategies. This is particularly important when dealing with infectious disease such as COVID-19, where mass interventions such as screening, social distancing, and vaccination can lead to effect at population level, including herd immunity, change in the infection rate, or even change in the pathogen ecology as a consequence of selective pressure. Different techniques exist to implement dynamic approaches to model the spread of infectious disease. Let's review together two of the most popular ones, namely agents-based models and the state-based susceptible infected remove model. Agent-based models are simulations composed of agents that interact with each other and their environment. Because each agent can make its own rules, this type of approach can capture aggregated phenomena derived from the behavior of single agents. These models offer a great explainability of the root causes, leading to the propagation of a disease, but are computationally intensive to run and thus hardly applicable to the large population. Indeed, the behavior and the interaction of each type of agent needs to be fully defined in order for the model to be useful. Furthermore, we can note that these rules are case-specific and are hardly transferable from one population to another. The second type of model that we will see together is the state-based susceptible infected remove model from the family of equation-based model, or SEER model for short. This is a state-based model where every state expresses the degree of exposure of a population to the disease. As the name of the family implies, the SEER model is equation-based where each population defines the rate to go from one state to the other. The SEER model thus separates the population into three groups and simulates the evolution over time of each one of the subpopulations. The transition rates are defined by the time scale to which an individual can transmit the disease, the time to recovery, and the number of newly infected people due to an infected individual. In other words, the parameters defining to which extent a subpopulation is susceptible to be converted to another over time is defined by the rate of transmission per contact, a recovery rate, and is bounded by the total population. The figure shows the typical shape of a SEER model over time. At t equals 0, none of the individuals in the population are infected and they are all susceptible for infection. Once the pathogen is introduced in the population, it starts to spread and the number of infectious people will increase, as well as the part of the population which recover from the disease and is now immune to the pathogen. Finally, after a certain period of time, in this case at t equals 2.5, enough people are immune to the pathogen, leading to herd immunity, where the pathogen is not able to contaminate new hosts anymore. Comparing both types of models, we see that they offer very different advantages and limitations. Indeed, the agent-based models allow for very fine-grained control over the population, enabling to have more diversity within a given population, both in terms of states of the agent and in the interaction that they can have with each other. However, such type of simulation is heavy and requires a lot of parameters that are hard to extract from observations. On the other hand, equation-based models offer less control over individuals but require far less knowledge about the population and thus less parameters. Furthermore, this type of model is much more computationally efficient and are easier to be extended, requiring just a few parameters optimization and eventually the addition of new transition rules. For this reason, in this work, we decided to work with equation-based models. However, we do not directly use the SEER model, but instead we use an extension, the SEI HCRD model, divided in 7 subpopulations. The first 3 populations are the ones that we already covered in the SEER model, which are susceptible, the number of people susceptible to be contaminated by the pathogen, infectious, the number of people that can transmit the virus, and recovered, the number of people that recovered from the disease and are now immune to the pathogen. Then we have the new subpopulations, the first being exposed, which is the number of people contaminated but not yet infectious, then hospitalized, which is the number of people infected that needed to be hospitalized, critical, which is the number of people infected, hospitalized and in critical conditions, and finally dead, which is the number of people that die as a result of the disease. Now, let's have a look at the system of ordinary differential equations defining this model. As we can see, we still have 3 equations defined by the SEER model, augmented by 4 new equations to represent the 4 new state transitions that are present in this extended version. Let's have a look at the parameters of those equations. In green, we see the transmission time estimated to transit from one subpopulation to another. These transmission times represent the average incubation period, the average infectious period, and the average hospitalization time for both normal states and critical states. On the other hand, in blue, we have another set of parameters that determine the severity of the infection. M is a percentage of infected individual with non-serious symptoms. In other words, the proportion of individuals that are asymptomatic or have mild symptoms after exposure to the virus and that are not hospitalized. C is the percentage of hospitalized persons who will eventually enter a critical state. And finally, F denotes the percentage of persons in the critical state who will pass away. In order to set the values for these parameters, we lean on Liu's et al. Work and assign them with constant values that you can see in the table. We can read this table as follows. The period of incubation of the virus is 5.6 days. People infected with the virus are infectious for a period of a bit less than 3 days. In average, someone developing a symptom is hospitalized for about 4 days in case he or she is malconditioned and 2 weeks when he or she is in a critical condition. As for the transmission ratios, they indicate that 80% of the people contracting the virus will not develop any serious symptoms. Among the 20% that are developing symptoms, in 10% it will be critical, and among those 10% critical, 30% will lead to fatalities. Coming back to the system of equations, we see that there is still a parameter that has not been defined yet, the effective reproduction rate, which is the number of people an infectious individual can contaminate over a time interval. However, as we can see by the suffix t, this parameter is dependent on the time. Therefore, in order to be able to resolve the system of equation, we need to express it in a form that is independent of the time. To do so, we represent the effective reproduction number as a Hill decay function and look for the best parameters k and l. We use the LBFGS optimization method to find the values of these parameters that minimize the mean square error of the number of cases and deaths predicted by the SEI-HCRD model over the one reported by the governmental institutions. Once the value for k and l are found, they can be injected in the Hill decay function to generate a time series for the past value of the effective reproduction number. At this point, we have a model that can simulate the evolution of the COVID-19 pandemic per country with a low mean square error in the past. However, this model in its current form presents two limitations. First, we made a strong assumption that the values for the effective reproduction number follow a Hill decay function. While true in the past, this might not be the case in the future. Second, the parameters used by the model do not allow to account for the different mitigation strategies that governments might implement. Hence, we need to represent the effective reproduction number in a way that allows to account for such decisions. In order to achieve that, we propose to represent the values for the effective reproduction number as a function of the mobility of the population. Since we now have a labeled dataset offered by our model with conjunction with past mobility data, we can learn this function using supervised machine learning methods. The mobility data are extracted from the COVID-19 Community Mobile Report provided by Google. It tracked the mobility trends over time for different categories of places in 97 different countries. Each feature corresponds to a category of places and its value captures the daily traffic of such places. More precisely, the value of the feature is the difference between the daily traffic and the traffic baseline. The report includes 6 categories: groceries and pharmacies, parks, transit stations, retail and recreation, residential and workplace. Of course, the value of these features are country-specific and are largely impacted by the mitigation strategy of each country. Here we can observe the trends for Italy and Luxembourg. We augment our feature set with demographic features such as the GDP, the size of the population density, etc. As for the mobility data, we augment them with the corresponding day of the week to take into account the weekly fluctuation of the data. Furthermore, the mobility features are augmented by smoothing over 5, 10, 15 and 30 days. Hence, each mobility feature corresponds to 4 inputs. Overall, our feature engineering process yields more than 4,000 inputs of 32 features each. Once a training set with expected values is established, a supervised model can be trained to predict the future values of the effective reproduction number using the mobility and demographic data as features. To do so, we investigate 3 types of supervised learners: a feed-forward neural network and a long short-term memory network for which we use a grid search to select the optimal hyperparameters, and a gradient boosting using 500 estimators. For each of the approaches, we evaluate the performances using the coefficient of determination and the root mean square error. While the long short-term memory network yields the best scores, we discard it since this type of model doesn't offer good explainability. The feed-forward neural network offers better scores than the gradient boosting, while both techniques offer explainability, thus we keep the former. Then we try different splits to test the ability of the feed-forward neural network to learn from different sources for the training. The results show that the knowledge acquired by the model is able to transfer from one country to another. At this point, we have a model that is capable of learning the effective reproduction number using only demographic data publicly available and mobility data provided by Google. It is now time to apply some scenarios to see how the prediction produced by our model behaved. So, we proceed to investigate 4 strategies for an exit from the lockdowns that were taking place all over the world. The goal of the exit strategies is to allow a return to normal activities while minimizing the impact of the number of deaths and avoiding peaks in hospitalization that would saturate healthcare facilities. The strategy that we are investigating are the following. First, hard exit, where all mobility activities are resumed to normal at once. Then, a progressive exit, where mobility activities are gradually restored with an increase of 15% of the activity every 2 weeks until the pre-lockdown activity level is reached. A cyclic exit, where every 2 weeks activity is resumed to normal, then brought back to lockdown situation. And finally, the statu quo, where the lockdown situation is maintained for the entirety of the period. As expected, when observing the fluctuation of the effective reproduction number on the right figure, we see no evolution from the initial value in the status quo case, a cyclic fluctuation in the case of cyclic exit, a soft increase when applying a progressive exit, and finally a brutal jump in the case of hard exit. The number of cases presented on the left figure is obtained by introducing the effective reproduction number computed back in the system of differential equations. We see that when applying a hard exit, the number adjusts as soon as the lockdown is stopped, while a progressive exit offers a delay and a cyclic exit exhibit different peaks. But what are the features that are influencing the results? To answer this question, we feed CHAP on the full dataset. On the figure, the distribution of each feature spans horizontally to inform on the impact of the feature on the final decision, while the color of each point of the distribution provides information on the range of values of the feature that have an impact. Red means negative, while blue indicates a positive contribution. By observing the figure, we can see, for instance, that for the feature transit station, higher values have a strong positive impact on the prediction. The same goes for the features related to retail and recreation activities. For transit, retail, and park features, the trend values over 5, 10, and 15 days counter the impact of the respective daily value, yet on a lower scale. This indicates an inertia phenomenon that can be explained by the actual delay between the actual number and the reported one, and also the delay inherent to the epidemiological model. Now that we have a model that can predict the evolution of the pandemic based on mobility data, which can be impacted by policies, we can find which is the optimal set of measures to be taken in order to minimize the socio-economical impact while minimizing at the same time the impact of the pandemic on the health sector. To achieve this goal, we rely on a genetic algorithm to find the best solution under a set of constraints. The objective of the genetic algorithm is to generate a policy schedule that the decision makers can follow. First, we use two fitness functions which represents the compromising health and societal impact of policy scheduled. Furthermore, for a policy schedule to be an acceptable solution, we require that the number of critical cases never exceeds the hospitalization capacity of the country of interest. Then, we rely on PIMO to implement our NSGA2 search and use the library's default value for the remaining parameters like the mutation rate or the crossovers. The result of this process is a set of optimal scenarios on the Pareto front solution presented in the form of policy schedules which correspond to when an activity should be set to a certain level in the form of a calendar. The figure on the top shows the evolution of the effective reproduction number when following the scenarios proposed by the search-based algorithm. In other words, the optimal scenarios. On the bottom figure, we can see the previous results from the handmade scenarios. As we can see, the optimal scenarios tend to keep the lockdown longer, lift it, then lock back partially the activity. Now, let's see how the different scenarios perform with respect to our objectives, namely minimizing the impact on the economy while limiting the effect of COVID-19 on the health of the populations. To do so, we use two metrics: the mobility area under curve, which reflects an economic objective that we need to maximize, and the number of deaths that obviously we are trying to minimize. In general, we see that the search algorithm in red yields better strategies than the man-made ones, both in terms of impact and activities and the number of deaths, while ensuring that the healthcare facilities are not overwhelmed. Indeed, by construction, the search-based solution only provides with strategies that are not exceeding the healthcare capacities and reject any solution that would. To sum it up, in this presentation, we have presented a toolkit that can generate optimal policy schedules for policymakers. The toolkit relies on mathematical modeling to compute the evolution of the pandemic, in particular a SCI-HRCD equation-based model. The effective reproduction number driving the transition between different subpopulations of the model is presented as a function of both mobility and demographic data. To compute this function, we rely on deep learning and more precisely on a feed-forward neural network. Hence, the model takes as input a schedule of measures influencing the mobility and output the evolution of the pandemic over time. Finally, we propose a search-based algorithm in order to compute the best policy schedule to help policymakers in their task of restoring economical activities while preserving public health. This leads to a toolkit that provides decision makers with the tooling necessary to provide sufficient insight as which exit strategies to take to mitigate in the best way this global crisis that every country is facing. And it is doing so for 97 countries. Before leaving, let me introduce our online platform that allows to generate in real-time policy schedules. The interface allows to choose policy schedules for a specific country. In this case, we choose Luxembourg. We can then choose a set of measures to apply. This consists in setting a degree of activity for a specific sector at a specific date. A value of 100% represents normal activity, while a value of 0% indicates total lockdown. In this example, we set the values of activity level at 70% of the normal level for workspace and outdoor activities. And then let's add 80% for public transport and retails. So for public transport, we set it to 80%, and for retails, set it to 80% as well. Then, when clicking on the play button, the model evaluates in real time the impact of the measure and outputs a graphic displaying the evolution of the pandemic. As we can see, the figure shows the evolution of different subpopulations of the SIE, HCDR, as well as the effective reproduction rates. This concludes this presentation. Thank you for your attention and feel free to visit our website to play with the tool.